Hello, everyone. So last time we looked at some set theory. We looked at set operations and some identities and properties, right? So last time, set operations and their properties. And we looked at some basic identities regarding properties of sets. And then we saw that, let's say, if you want to prove an identity of this type, you can take an element in the left-hand side and show that that element must be in the right-hand side. And then take an element in the right-hand side, show that it has to be in the left-hand side. This will show that the left-hand side is a subset of right-hand side, and right-hand side is a subset of left-hand side. And once you do that, then we can conclude that left-hand side and right-hand side must be equal to each other. Okay, so let's look at another example. So this example is one of the book exercises, question 20, page 144. Show that for any sets A and B, we have B minus A. So we use the set difference with this notation. Your book uses this notation, but we use this notation. Let me use the notation that we used before, B minus A union. So this is actually part E. B minus A union C minus A equals B union C minus A. So we want to prove this identity. Of course, one way to do this is to show that left-hand, take element, the left-hand side, show that it's a subset of right-hand side, and right-hand side is a subset of left-hand side. So that's one way to do it, but we can also use the other identities that we learned before to try to prove this identity. So you're allowed to use previous identities always to prove new identities. So let me start with the left-hand side. Left-hand side. So this is B minus A. We saw one of the identities was saying that B minus A same as B intersection A complement, and then union C minus A means C intersection A complement. Now, how can I simplify this? If you look at this, I can use distributive property, right? So to write this one as A bar intersection B union C using distributive property, right? Distributive property says that A bar intersection bracket B union C is same as A bar intersection B union A bar intersection C. And now this is same as the commutative property. I can write this one as B union C intersection A bar. And then this is same as B union C minus A. Again, because the property that we saw before was saying that D intersection A bar is same as D minus A for any set D. Now my D here is B union C, and this is same as right-hand side. So this is basically solution one, let me say. Solution two, as I said, taking elements. Taking elements, what do I mean by taking elements? Take an element in the left-hand side, show that it has to be in the right-hand side. Then take element in the right-hand side, show that in the left, show that it has to be in the left-hand side. So let me leave this one as exercise, okay? All right, so these are the methods that you can use to prove identities in set theory. Now, the next topic we want to look at is generalized unions and intersections. So next we look at generalized unions and intersections. Well, so far we have defined a union and intersection of finitely many sets, right? So far, A1 union to AN, and let's say A1 intersection to AN have been defined. Next, we define union and intersection of infinitely many sets. So if we have finitely many sets, we know what to do. Union means the set of all elements X, where X appears in at least one of the sets. And for intersection, set of all element X, where X appears in all elements, in all the sets, AIs. But what should we do for the union or intersection of infinitely many sets? So definition, let I be an index set For example, we can set I to be n, the set of natural numbers. Then a union AI, I belongs to I, is defined as follows. So union AI, I belongs to I, is defined as set of all X, such that there exists I in I, with X belongs to AI. So very similar definition to union of finitely many sets. Right? Union of AIs is the set of all elements X where X appears in at least one of the AIs. When we say there exists I in I with X belongs to I, means X appears in at least one of the AIs. And what about the intersection AI? So we say similarly, let me say also intersection AI, I belongs to I, is defined as follows. Intersection AI, I belongs to I, is equal to the set of all X, such that for every I in I, X belongs to AI. So it's the set of all elements X where X appears in every one of the AI, every possible AI. Okay, let's look at some examples. Or let me, before giving the example, let me consider the case where the index set is natural number, like I said. So in particular, if I is equal to a set of natural numbers, then union AI, I belongs to N, is also denoted with union I from 1 to infinity AI. And then this is set of all elements X where there exists, such that there exists I in N with X belongs to AI. And intersection AI, I belongs to N, is also denoted with intersection I from 1 to infinity AI. And let's define that set of all elements X where for every I in N, X belongs to AI. Okay, so in the case where the index set capital I is natural numbers, union AI, I belongs to N is also denoted with union AI, I from 1 to infinity, and similarly for the intersection. Okay, and the definition is still same as before. Now let's look at an example. Let AI, let's say, equal to 0 to I. AI equals 0 to I. Find union AI, I from 1 to infinity, and intersection AI, I from 1 to infinity. So let's get some idea about these AIs. So let's look at the real line. Well, let's say this is 0, this is 1, this is 2, this is 3, and so on. Now for A1, AI is the interval from 0 to I. So A1 is from the interval from 0 to 1. So this is your A1. And then A2 is from 0 to 2. And then A3 is from 0 to 3, and so on. Okay, now what is the union here? So let me say the claim is that a union AI, I from 1 to infinity. So what do you think the union would be? So we are taking the interval 0 to 1, then union 0 to 2, union 0 to 3, and so on. Now let's say, for example, if I had only 3 of them, 0 to 1, union 0 to 2, union 0 to 3. What is it? In that case, obviously the answer is 0 to 3. If I take 4 of them, let's say, then 0 to 4. 5 of them, 0 to 5. Now, if you continue this all the way to infinity, the answer is going to be 0 to infinity. The set of all non-negative numbers. Now, how can I prove this? How can I prove this? Well, I want to show that these two sets are equal to each other, right? So how can I show that two sets are equal to each other? We just said in the beginning of today, also last time, that we can take one element, the left-hand side, show that it has to be in the right-hand side, and take an element, the right-hand side, show that it has to be in the left-hand side. So to prove the claim, let's say X belongs to union AI, I from 1 to infinity. Then by definition of union, generalized union, what can I say? What was the definition of union AI, I from 1 to infinity? The set of all elements X, where X belongs to at least one of the AIs. Now I'm taking X inside my union, so that means X is inside at least one of these AIs, so there exists I in N, such that X belongs to AI, and AI, well, let me say J because I is already used. And AJ was 0 to J, right? By definition of AI is 0 to I, so AJ is 0 to J. And that means X belongs to 0 to infinity. Because any interval of the form 0 to J, obviously, for a fixed J is positive integer. Remember, J is positive integer. So any interval of the form 0 to J is obviously a subset of 0 to infinity. So if X is inside 0 to J, it will be also inside 0 to infinity. So I took one element the left-hand side, show that it has to be in the right-hand side. Next, take x in the right-hand side. And I want to show that it has to be in the left-hand side. How can I do that? So see, look at the real line again. This is 0 and all the way to infinity. So I'm taking some x here. I want to say that x is inside at least one of these AIs. AI is the interval from 0 to I, right? So how can I show that x is inside at least one of these AIs? I just need to take or choose an integer which is bigger than x, and then x will be smaller than that integer and therefore will be between 0 to that integer, which means it's inside in one of the AIs. Remember, AI is the interval from 0 to I. So once I find an element or integer I, which is bigger than x, then 0 to I will include x. So let me say, for example, let's say J2, for example, bigger than J. I just need to choose such number. So choose J2 in N such that J2 is bigger than X. Like the picture. No matter how large X is, I can always choose an integer bigger than X. If you're interested to know why, well, this is something that you will learn in analysis course. This will be proved in Math 225, Analysis 1. If you want to know why there exists always, I mean, intuitively, it's obvious, no matter how large your real number is, there's always an integer bigger than that, right? For example, if your integer is 10,000.20, you can choose 10,001, which is an integer bigger than x. But why there exists always such x? What's the proof for that? There exists always such J2. The proof will be given in Analysis 1, Math 225. So choose J2 such that this, and then x will belong to 0 to J2, and this is by definition A J2. So x belongs to one of the AIs, and that means x belongs to the union of all of them as well. And that's all we wanted to show. Okay, so as an exercise, I can leave to show that the intersection of AI, I from 1 to infinity, will be 0 to 1. Again, intuitively is obvious, right? Intersection means common elements. What are the common elements between A1, A2, A3, A4, all the way to infinity? So the common elements is this interval 0 to 1. But again, if you want to prove this formally, take x in the left-hand side, show that it has to be in the right-hand side. Take something in the right-hand side, show that it has to be in the left-hand side. Another example, let AI, let's say, equal to 0 to 1 over I. For I in N. Show that intersection of AI, I from 1 to infinity, is equal to, what do you think it is? Let's look at the real line again. This is 0. This is, let's say, 1. This is 1/2. So this is 1/3 and so on. Now let's look at the sets that we have. AI is from 0 to 1 over I. So A1 will be from 0 to 1. A2 is from 0 to, so this is A1. A2 is from 0 to 1 over 2. A3 is from 0 to 1 over 3. And so on. So what are the common elements? The common elements between all these sets. Well, for example, numbers bigger than 1/2 are not in the intersection because they are not in A2. If something wants to be intersection, it has to be in all of the sets that we have. Similarly, numbers bigger than 1/3 cannot be in the intersection because they are not in A3. Similarly, numbers bigger than A4, A1 over 4 cannot be in the intersection. So what is left? What is going to be left for me? The answer is nothing. Because the sets get smaller and smaller in each step. And you could say, or maybe you could guess, well, 0 will be left for me because 0 and no positive number will become less than 0 or even equal to 0. But the thing is, 0 is not included in any of the sets because all the sets are open interval by definition. Yes, if it was closed interval 0 to 1 over I, then the intersection would be 0, just the number 0. But because even 0 is not included in any of the AIs, therefore in the intersection, I will have nothing left, and the answer will be empty set. So how can I prove this now? So this was the idea that, we use the real line to guess basically what the answer should be, but now we have to prove it. How can I prove it? So proof by contradiction. I want to show that this intersection is empty. Well, what happens if it's not? So suppose that intersection AI, I from 1 to infinity, is not equal to the empty set. But if it's not the empty set, then it will have at least one element, right? So then there exists X inside the intersection. Now, X is inside all the AIs, right? So that means for every I in N, X belongs to AI. So in particular, X belongs to A1, which is 0 to 1. And that means, of course, X has to be positive. If X is inside the intersection, it has to be in all of them. And of course, in particular, in the first one as well. But what is the first one? A1 is 0 to 1. You can also see in the picture. So if X is between 0 to 1 means in particular, it has to be positive. So now choose J1, let's say, in N, such that 1 over J1 is less than X. See, no matter X, remember I already know that X is a positive number. Now, no matter how small this not positive number is, there is always a number of the form 1 over an integer, which becomes less than X. let's say, for example, even if x is not small, for example, if x is 5, for example, 1/2 will be less than 5. Or if it's 6, again, 1/2 is less than 6. But even if it's small, for example, 0.0001, I can say 1/10 million, for example, is still less than 0.0001. If x is 1/10 million itself, I can say 1/10 billion is less than x, and so on. So intuitively, we can see that there's always an integer j with 1/j less than x. But again, if you are interested in the proof, again, the proof will be done in analysis course or Math 225. So again, the proof of existence of such integer will be done in Math 225. All right. Now, what can I say then? 1/j1 is less than x. So that means, see, 1/j1 is less than x. So that means x will not belong to 0 to 1/j1, which is my aj1. If x is bigger than 1/j1, x, of course, will not belong to the interval 0 to 1/j1. See, this is 0, this is 1/j1, and this is x. So you can also see in the picture that x does not belong to 0 to 1/j1. And this is contradiction with x belongs to ai for every I in n. Remember, we were supposed to have x belong to ai for every I in n, but right now I found the number j1 where x does not belong to aj1. So this contradiction proves that intersection of I from 1 to infinity is equal to the empty set. So this is about the intersection of these sets. What can we say about the union of these sets? You can do that as an exercise. The union would be, so 0. So what do you think? 0 to 1, 0 to 1/2, 0 to 1/3, 0 to 1/4. So the union would be the elements that are at least in one of them. Well, that's very easy to guess because A2 is a subset of A1, A3 is a subset of A2, and so on. So if we take the union, we get the biggest set that contains all other sets, and that is A1, right? Because A2 is subset of A1, A3 is subset of A2, and so on. So we can use this argument to show that. So exercise, show that union I from 1 to infinity is equal to 0 to 1, which is equal to A1. All right, so let's start the next topic, which is 2.3, and that's about functions. So what is a function? Of course, you know you have seen functions before in high school and also in pre-calculus. But again, let's remind ourselves quickly, what's the definition of a function? So definition, a function is a rule, right, that assigns exactly one output, to every input. So each function, as you know, it has inputs and outputs, and it has to assign exactly one output to each input. In other words, it's not allowed to assign two outputs to one input. So the set of all inputs is called the domain, right? The domain of the function. And the set of all outputs is called the range. The range of the function. A set containing the range is called the codomain of the function. So the notation that we normally use is, we can say f from A to B and here A is assumed to be, so A is equal to df equals domain, and B is codomain. So codomain means what? Means a set containing the range. That's how I define codomain. See, I said a set containing the range is called the codomain of the function. So when we say f from A to B, so this is how we read it. We say f from A to B. A is assumed to be the domain itself. B is assumed to be the codomain. Codomain means either it's the range itself or it's a set bigger than the range, meaning that the range is a subset of B. So B is codomain, meaning that Rf, which is the range of F, is a subset of B. So a subset of B means it could be B itself or it could be something smaller. So for example, let's say the height of students in Math 120 class. Math 120 flex section class. So here, the inputs will be the students, right? Student 1, student 2. And outputs will be their heights. So student 1, for example, is 160 centimeters. Student 2, let's say 162 centimeter, and so on. So each input here inputs are students. So each student has exactly one height, right? So that's how we decide whether something is a function or no. We want to know whether exactly one output is assigned to every input. And here every student has exactly one number as his or her height. So we can say that we have a function here. So I can say exactly one output is assigned to each input. And that means we have a function. We have a function. Now the ways to represent a function. Ways to represent We can use a table or we can use diagram, for example, using table or diagram. Let's say, for example, we can sometimes say it this way. We can say, for example, this is A, this is B, and then this is F. So this notation or this diagram is used to say that or imply that F takes the elements of the set A to elements of B, and to each input A assigns exactly one output, let's say small b in capital B. Let's say, for example, you have A1, and then here we have B1, so which is, let's say, F of A1. And then let's say we have A2, which goes to B2. And let's say B2, which is F of A2. And so on. So when we say F of A2, means the output corresponding to the input A2. So when you say F of X, means X is the input, F of X is your output. So you can use table or diagram like this. And we can also use a formula. So the second option, using formulas. So when you say, for example, y equals f of x, so this means this is the input, and then this is the f of x, or which is same as y, is the output. So for example, let's say if you have f of x equals, or let's say f from, let's say, n to n, f of x equals x squared. So f from n to n, so we said that this means that this is the domain and this is the codomain. And f of x equals x squared means what? Means each output can be found by squaring the corresponding input. And what are the inputs? Inputs are 0, 1, 2, 3. And then the outputs, because remember in your book, n is defined as 0, 1, 2, 3 all the way to infinity. So the outputs, now how do we find the outputs? F of x is x squared. So each output can be found by input the square. So the first input is 0. So the first output will be 0 squared, which is 0. The second input is 1. So the second output is 1 squared, which is 1. Third input is 2. Third output will be 2 squared, which is 4. And then 9, and so on. So what is the range? Thus, the range of this function is given by, what will be the range? Rf equals 0, 1, 4, 9, and so on. So these are the outputs. So the range is 0, 1, 4, 9, all the way to infinity. Okay. So then we can talk about addition and multiplication of two functions. So addition and multiplication. So given two functions, let's say f from a to r and g from b to r and g from also a to r. One can define f plus g, and let's say c times f, and f times g as follows. So f plus g will be a function from a to r again. So remember, when you want to introduce a function, each function can be defined using its formula and also its domain. So if you just specify the formula, it's not enough. You also need to specify the domain. If the domain has not been specified, then you sign pre-calculus that you have to consider the largest possible domain, also called as a natural domain. So natural domain means the largest possible domain. Largest possible domain means what? Means the set of all numbers for which the function is not undefined. For example, the denominator is not 0, or under the square root is not negative. So finding natural domain is a topic that you sign pre-calculus. I don't want to go into details. For now, I just want you to pay attention to the fact that if you want to introduce a function, you need to introduce the formula and also the domain. So f and g, let's say, are from a to r, so the domain is a. So I want to introduce a new function called f plus g, the addition of those functions. F plus g is also a function with domain a, codomain r, and what is the formula? And f plus g of x, let's say if the input is x, f plus g on x is defined as f of x plus g of x. Similarly, c times f will be also from a to r. Again, the domain, I have to introduce the domain from a to r, and c times f on x is same as c times f of x, and also f times g from a to r. F times g of x is defined as f of x times g of x. Okay, so for example, let's say f from r to r, f of x equals x squared plus 3x, g from r to r, g of x equals x squared plus 5x. Find f plus g. So what is f plus g going to be? So f plus g will be also from r to r, right? Because the domain of f and g are both r, so domain of f plus g will be also r. And f plus g of x will be same as f of x plus g of x, and that's going to be x squared plus 3x plus x squared plus 5x, and that's going to be 2x squared plus 8x. Okay.